Hi, my name is Isaac Gerg, and I'm a PhD student at Penn State University under the supervision of Dr. Vishal Manga. I'd like to present my work entitled A Learnable Image Compression Scheme for Synthetic Aperture Sonar, or SAS imagery. SAS imagery is typically collected with an autonomous underwater vehicle, or AUV. While an AUV survey is ongoing, rarely is imagery sent in real time to topside operators. In fact, often the imagery is only examined once the vehicle completes its survey and returns topside. This is the result of having a low bandwidth acoustic communications, or ACOMS link, between the topside operator and the AUV. This link tops out at about 5 kilobits per second. In this work, we posit that the limited ACOMS bandwidth is only part of the problem as to why no imagery is sent to topside operators. Commonly used off-the-shelf compression schemes such as JPEG and WebP are often used in compressing SAS imagery, but do so inefficiently because these schemes were primarily designed to compress natural imagery, which has very different statistics than SAS imagery. We see here the wavelet coefficients for the vertical and horizontal bands of SAS imagery along with natural imagery. We notice two specific differences between the SAS and natural images. One, the SAS statistics have asymmetric tails between the vertical and horizontal bands. And two, the distribution of natural imagery has a much more defined peak than the SAS imagery. We will account for these important differences in our method. So, in this work, we create our own learned image compression scheme, which is tailored for SAS imagery. To do this, we leverage the work of Belay et al. 2017 and create a convolutional neural network to learn, quantize, and compress SAS imagery. Additionally, we specify a probability model for each feature layer, which we call this the feature-dependent model, which is to account for the asymmetric image statistics we see in SAS imagery. Our model is given a database of SAS imagery and a target bitrate to achieve and is trained for 5,000 epochs. We create two methods, one which models the probability of the quantized symbols for each feature channel independently, and one which models them all simultaneously. Let's look at results. Here we show the compression rate as bits per pixel on the x-axis and image fidelity on the y-axis. Ideally, we want all points in this top left corner, which signifies best image quality and lowest bitrate. We compare our methods to several popular off-the-shelf methods, which are shown by this Pareto front here. We then show results for our two methods at 5 specific bit rates. Zooming in on this section of the plot, we can see that our method is able to reduce the bit rate of the SAS imagery from 30 to 35% while still maintaining good image quality. Finally, let's take a look at a few examples. On the top row, I show results of a SAS image compressed by JPEG, our deep neural network at 0.6 and at 1.4 bits per pixel. I also show the uncompressed image for reference, which is encoded as a ping. The second row of the zoom is the middle from each corresponding image above. What we can see is that the JPEG compression exhibits blocky artifacts at the native resolution of the image, and that our two deep learn methods more resemble the uncompressed lossless image. Looking at an image with sand ripple, we see similar performance. JPEG has blocky artifacts at the native resolution, while our method more resembles the uncompressed lossless version of the image. With that, I thank you for your time. I conclude, and I will take any questions.